So my topic today will be covering transitions in strongly correlated materials. So, but this topic is a bit too broad, and I will focus on some recent advances in this field related to the development and applications of LDA plus DMFT methods. So, of course, I'm indebted to my collaborators and co-authors from place where I'm working, Institute of Metal Physics and Ural-Federal University in Yekaterinburg, Russia. Also to Jan Kunish from Prague, previously in Augsburg, Germany, and of course to our collaborator, strong collaborator, and one of the founder of DMFT methods, Dieter Volkhardt from Augsburg University in Germany. And I work in group of Professor Vladimir Anisimov, and he will make a very detailed lecture on theoretical method developments from DFT theory to LDA plus U and LDA plus DMFT methods a bit later today. So I will skip a part of theoretical description for these methods and fields of their application, just concentrate on some physical effects which we are really interested in, considering spin and MIT metal to insulator transitions in strongly correlated systems. So the main feature, the main property of these transitions is that at some extent, at some conditions, you have a metal, and then changing some external conditions like pressure or temperature or chemical composition, you can finally get to an insulator. And of course, this phenomena was at the front edge of investigations for many years, for like 20 last years. And recent advances in this field are related with the development and applications of LDA plus DMFT methods. So what's the strength of this method? So here, if we consider a continuous transition from metal into insulator, one can find experimentally and theoretically very different situations. So first, when the bandwidth is rather large and correlation strength, U value, is small, we arrive at the very common situation of fully or partially filled band, itinerant states, and these states are coherent, and these are quasi-particles just at the Fermi level. So in some simple metals, we have this situation. So, and on the other side of this transition, we have only incoherent states, and so the Fermi energy goes somewhere in between, and these states are characterized by strong electronic correlations with the U value over W, the bandwidth, like 2 or even more. And of course, the very precious situation is somewhere in the middle, because we have a continuous transition, but it doesn't go like a direct separation of one band into two bands, but it goes with the formation of quasi-particle peak at the Fermi energy. It corresponds to this situation when we actually have two kinds of states, incoherent states, so-called Hubbard bands, just shifted from the Fermi level, and some states at the Fermi level characterized by coherent states, coherent quasi-particles, just directly at the Fermi level. So you can look at a brief, very brief paper by two founders of DMFT methods, Gabriel Cutler and Dieter Volkert, and they review some very important physical aspects of this DMFT methods, because it allows to go continuously from either ways actually to the other side. And so it was a great advantage of the LDA plus DMFT scheme when this physics, actually described by dynamical mean field theory, was included and merged with ab initio codes, and finally we get to the point where we are now, and what can we do with these methods. So another physical aspect I want to draw your attention to are so-called charge transfer insulators. So as most of systems with strongly strong correlations, these are oxide systems of transition metals, 3D metals. And historically, they were first to investigate, and of course, they form a wide group of compounds, very interesting and important for applications and future developments of the materials. So one of the main aspects was emphasized by Zanin, Zawadzki, Allen in their very famous paper, and they drew the attention from the experimental point that in some systems the transition, metal to insulator transition, goes eventually differently than in all others because of the composition of the upper shell, 3D shell, and oxygen P shell directed just at or near the Fermi energy. So in oxide systems with nickel and copper, there are oxygen 2p states that occur at or mix with lower Hubbard band. This is a band formed by 3D electrons, 3D states of nickel or copper, and this U value that separates upper Hubbard band, also 3D states, and lower Hubbard bands is much larger than the splitting between these oxygen P states and upper Hubbard band. So this line corresponds to the Fermi energy, Fermi level. In contrast to another class of compounds, titanium or vanadium oxide, where its gap is proportional to the U value, and oxygen P states are thrown away and can be omitted in all calculations and theoretical considerations because they have very weak coupling and hybridization with the 3D states or other correlated states near the Fermi energy. Okay, so before LDA plus DMFT development, there was absolutely there were some problems concerning with the reproduction of this separation, and for many compounds this problem was solved employing LDA plus U method that used U value to separate this occupied and empty correlated states and produce well this energy gap. So in many compounds, this method is used nowadays and in very good agreement with the experimental data. But unfortunately, LDA plus U methods can't handle this situation except for some tricks. I'm not going to discuss them, so maybe in the presentation of Vladimir Anisimov there will be some idea about it. Okay, so this slide, I want to show you some first results, so these results were obtained in 2007 for nickel oxide, and actually in that paper, LDA plus DMFT method was used to reproduce charge transfer nature of an insulator in nickel oxide. So we need to start with this example because in order to describe properly a transition from an insulator to metal or otherwise, you need to be sure that you reproduce both sides correctly and can go continuously from one to another. So if one sees this inside, it shows actually LDA result for 3D nickel band split it into T2G and EG orbitals, triple and twice degenerate in red and black. So you can check this capture, and also green states corresponding to oxygen 2p states. So as one can see in LD, nickel oxide is a metal. That is contradicting to the experiments. Of course, you can check this for the emission results. And in LDA plus DMFT, there is another advantage of this method, that it can be used in a paramagnetic state in contrast to LDA plus U, for example, or some other states that cannot handle this method. So these results were obtained for a temperature above the Néel temperature in nickel oxide, and shows that upper Hubbard band in these results were obtained to almost completely formed by EG states of 3D orbitals of nickel. But this valence band, it has a mixture of T2G and EG states, and the main result here was that the upper part of this valence band is formed by a mixture of EG states and oxygen 2p states. And that's actually what is seen in the experiments. So if one have a look onto this photoemission spectra, these are taken in different energies, so the higher energy result corresponds to nickel 3D states mostly, and the lower, for the lower temperature, for the low energy, corresponds to oxygen 2p states. So one can see that just below the Fermi energy, these states are mixed. So, and actually taking into account experimental resolution, we finally obtained to a very similar picture here. In order to further represent this charge transfer nature of this insulator, we also considered a situation when we doped this nickel oxide. So doping with a hole, it's 0.6 and 1.2 holes, and these are the summing density, spectral function, spectral density of states. It's finally gets to the situation when these states, just at the Fermi level or nearby it are also formed by oxygen 2p states and nickel 3D, and in particular EG states. And this situation is seen in the experiment and cannot be reproduced by LDA+U and many other methods. So in this table, it illustrates how this doping with a hole works. So actually, it goes like EG and T2G states, they decrease a little bit, but also there is a decrease in the occupancy of oxygen 2p states. Okay, so after that, we were settled to handle a bit more complex system, but similar, taking into account charge transfer nature of an insulator. Oh, yeah. So, and this is the comparison of reciprocal space distribution of states. So experimental, and experiments are this dashed and circles and triangles, and this underground picture is the dispersion obtained from LDA+DMFT result for it. Okay. At that time, we didn't know actually that in nickel oxide at very high pressures there is an insulated to metal transition. But very recently, some colleagues, some Russian scientists also, they participated in this research. They found that there is a transition. And because we didn't know that, we switched onto manganese oxide. And first of all, because there is a metal to insulated to metal transition and spin transition from a high spin to low spin configuration in it. And of course, it was a great challenge to reproduce both these transitions, as I told you before, because of discrepancies of the methods used at that time. So the first result is shown here. So this is a final density of state spectral function calculated from LDA+DMFT methods in comparison with experimental results. And this graph shows results for applying pressure onto this compound. So as one can see, being an insulator makes for manganese oxide that EG states are separated by some value, and T2G states are also separated by some value, and they form a mixture in the conduction and valence band. Applying pressure, so one can get to a situation at some volume, just as a half of an experimental value at ambient pressure, when EG states are almost empty and T2G states are fulfilled. So it corresponds to the following theoretical situation, that at ambient pressure, here we have a high spin configuration because we have 5d electron in manganese oxide 3D shell. And applying pressure, we go into this low spin configuration where we have a low spin value, and all 5 electrons, they are moved onto T2G states, and EG states goes up. Yeah, so, and correspondence to the experiment is the following, that in the experiment, this spin and metal to insulated to metal transition occurs at volume range approximately from 0.6 to 0.7 in this region. It's transition. And theoretically, we also reproduced this transition in a correct range, and also made the following interpretation. So magnetically, this states corresponding to ambient pressure. So it has a very large value of magnetic moment, like 5 or like 4.5 megaton Bohr, and it corresponds to the orbital occupancy of T2G states and EG states almost equal. And so this transition goes like this, resulting in a low spin configuration with magnetic moment approximately 1 megaton Bohr. So, and it makes very different occupancy for T2G and EG states. Okay, so this effect was ascribed to not just to a change of the bandwidth, but also it has a so-called orbital selective Mott transition nature, because it makes differently for T2G and EG states. So it makes orbital selections here. Similar situation was then later found in cobalt oxide, and so these results are they correspond to the LDA calculation. So it's again a metal in usual DFT calculations, and one needs to apply LDA plus DMFT methods to reproduce its insulator nature. And again, at ambient pressure, it's a mixture that continuously go into a metallic situation, and this pressure range approximately from 40 to 70 or maybe a bit higher GPa, it again agrees with the experimental results. Okay, and for this compound we also analyzed the occupation numbers and magnetic moment. So here magnetic moment is a bit smaller than, no, sorry, yeah, so it's like less than 3 megaton Bohr, and it goes to a bit higher values, while this occupancies that change in this way. So analysis of possible configurations make it possible to conclude that this transition goes from high spin state that is 5 and 2 electrons into T2G and EG states into just lower states. So these probabilities are high here, but probabilities for states with the lower occupancy of EG states are higher in this region of pressure. So another interesting example of spin transition under pressure was considered in these compounds, and so here one can see how it changes in hematite mineral. So it goes with the formation of this interesting peak just very close to the Fermi level. Okay, so again, this figure analyzes the occupancy and their change under pressure, and shows that in this compound, on contrary with manganese oxide, it goes with the coexistence of two states actually. So one can find for, sorry, for some pressures one can find lower or higher spin states in here. Okay. Okay, so it's possible to estimate different temperature ranges for this calculation, because LDA plus DMFT allows to include electronic temperature into calculation. So some very interesting phase diagram can be formed based on them. Yeah, so also another example, so just last final. In iron monoxide, in agreement with experimenters, we believe, we found applying these methods under pressure that there is a metallization of the spectra, but spin transition doesn't happen, and all the occupancy, they are preserved at their level, and magnetic moment doesn't change drastically. Yeah, because it's another spin configuration, and physics a bit different here. This phenomena are very interesting, and I believe they provide good opportunities for future developments of new materials and switching devices. And recent developments in LDA plus DMFT scheme allowed us to investigate, in good agreement with experiment, different metal to insulator transitions and spin transitions into oxide systems of transition metals. And for some systems, we're making calculations now for systems with iron, oxygen, and other elements where no experimental data available, like materials in the low mantle of the Earth. And we believe this will allow us to make some prediction for magnetic state of these compounds depending on their structure and applied pressure. Okay, thank you very much for your attention.
We have a few minutes for some questions, please.
Most cases of you presented have a very small unit cell. How large could be unit cell for acceptable time of simulation?
So Professor Anisimov will describe this scheme in detail, but I want to say that in this scheme, it's really important how many correlated sites and correlated orbitals do you have at your system. For example, if you have only one correlated ion like iron or nickel, and you can even maybe minimize the set of orbitals you consider as correlated, because at low symmetry you can just restrict yourself to T2G or EG states, just throwing all the rest. And this scheme, mostly DMFT methods that uses quantum Monte Carlo simulation to deal with the impurity problem, it depends on these results. And now this scheme evaluates evolution. It goes its evolution into the direction of many impurities and many types of ions, interacting ions in the system. So, but also answering to your question, there are some extension considering a lattice, like a square lattice of interacting ions, and like 10 or 20, it's doable. People can make it.
Any more questions? Please.
So, since we're nice talk, and can you go to the slide of metallization of yeah.
This one, yeah.
Well, the pressure-induced metallization, why did the thin rubber, they have high pressure, so high density? Which kind of state?
You mean states, this quasi-particle peak, or? Yeah, so in this crystal is of very high symmetry, so T2G states are degenerate. and all three T2G states, they form the same degenerate three spectral functions.
But looks like really half field. I mean, the occupied electron.
No, actually it's not. You can see the occupancy. It's in blue here, so it's like around 2. So it corresponds to the right, and this one. So it's 2 and 2 something. So and you can see it's asymmetric here, definitely.